Hello everyone. In this video we will talk about projection operators, and this is one of the most important operators that you will use in quantum computing. So it's very important to understand what it is actually. Okay, so let's try to understand that. First, let's try to understand it with an example, and then we can go to the general case. So let's say that psi is a quantum state of a qubit. So I can write it as A0 plus B1. In general, A and B are complex numbers, right? So as I showed you in one of the discussions, that I can think of this. I mean, when A and B are real, that gives you the picture that this direction, the x direction in the conventional sense, is your 0 vector direction, and the y direction in the conventional sense is your 1 vector direction. All right, then any psi will give you a here and a b here, right? This is how you picturize these vectors. And now I want to check what is this operator. As I've mentioned in the last video, that these are operators, these are maps, linear maps, right? So let's see how does this operator work on psi. All right, so this operator acting on psi gives me something like this, right? And if I write it down explicitly, then I'll see that this is nothing but a times 0 plus b times 1, right? So this is a linear map, so this is a linear operator, so I can distribute it over the terms in the parenthesis. So I can write a 0 0 and a 0 plus b 0 0 and a 1. And you know from the orthogonality property that and as zeros are normalized, this is equal to 1, this inner product, and from orthogonality property this is 0, because 0 and 1 are orthogonal. That means the angle between them is 90 degrees, and so you know that, I mean, a dot b is equal to 0 when a is perpendicular to b, right? So as 0 and 1 are perpendicular to each other, or in a more general sense they're orthogonal to each other, then their inner product is 0. So what are we left with? So we are left with just a times 0. Okay, so what you can see is that you have this psi, which is a combination of this and this, which is this vector is in the x direction, this vector is in the y direction. All right, and your psi is in general a combination of a superposition of these two vectors, right? But what this operator 0 0 is doing is that it is just keeping the part that is in the direction of 0. All right, so now if psi is a times 0 plus b times 1, then I can say that if this operator works here, acts on this psi, then what you get is nothing but b times 1. So this is projecting you to the 1 direction. Okay, this is projecting you to the 0 direction, this is projecting you to the 1 direction. So these are projection operators. Okay, these operators acts on a vector, any general vector psi, and it projects only the component in the direction of the projection operator. That means if you are doing it in the 0 0, then it will only take the component in 0 direction, right? But what if I don't take 0 0 or 1 1? What if I take something else, in some general vector? Then what happens? Then let me draw the picture again. So you have this 0 and you have this 1, and now let's say you have a state psi like before, but now I have another vector which is v. Okay, and now I want to check is that what is the value of what does it do on psi. Then the answer is, okay, as you can guess from in the experience before, is that this will take a projection of psi in this v direction. All right, but let's try to prove it. And there is one more assumption, that is v is normalized. That means the norm of v is equal to 1. Okay, we have assumed that this is a unit vector. So if v outer product v acts on psi, then what happens? What happens is that we will write it down again, v, and you have a 0 plus b 1. Okay, that's very good. And then what I can write, as it is a linear operator, as you know, that this is nothing but v, and you have this v on 0 plus b, you have v 1. All right, now you can see that this and this and this, these four are just numbers, because this is an inner product, this one is an inner product, and this is a number, and a and b were numbers by definition. So what you can write is obviously a v0, which is the projection of the 0 component of the psi vector in v direction, plus b v1, which is the projection of the 1 component in the v direction, and what you're left with is just v. So it is proved that this is a vector in v direction only, and this is nothing but the projection of psi that we claimed in the very beginning, that this is just the projection of psi in v direction. All right, so so the conclusion is that, so the conclusion is that these vectors are projection operators, and what it does, okay, projection operator would be the right word, yes, and what it does is that it projects any vector. When it acts on it, it projects any vector in the v direction. All right, but there is also one assumption, that is v times v is equal to 1. That means it's normalized. All right, now what we can do, let's check one more property. Let's call this pi v. Okay, whenever I use this capital pi v, that means it's this operator. Okay, this is a definition that we're using. Now let's check what happens if I act pi v twice. So let's look at it intuitively first. That is, you have this psi vector and you want to take the projection in 0 direction. Okay, then what you get is just a0, right? This is the vector you're left with if you act on psi with pi v once, pi 0 once, right? You're acting with pi 0. Now if you act on this vector again with another pi 0, it will not change anything, because okay, if you have this vector, let's say this is a vector 0, if you take this in, if you take the projection of this vector again in this direction, you will just get that, right? So So what do you expect from here? If you act on the projection operator twice, this means nothing but acting on the vector once. It is the same thing. Let's try to prove that. Okay, so what we will prove from there is that there's no difference if you act on it act on the vector once or twice with the same projection operator. All right, let's check that. So if you know, for by definition this is v, right? And now let's calculate the left hand side. Left hand side is equal to v, and you have again v. But by definition this is 1 because this is a normal vector. Then what you're left with is just v, and which is equal to the right hand side. All right, so what we have proved is that pi v square is equal to pi v. This is one of the most important properties of projection operators. All right, so now one more property. This is also very important. Let's look at the example again. Let's say this is psi. This is your 0, this is your 1. Okay, now I say that I act with the projection operator in 0 direction on psi. Then what I get is just 8, 0, right? But now if I act on this vector again with pi 1, that means I want the projection in the 1 direction. After taking it in the 0 direction, what do I get? So if you look at the picture, if you act on the vector with the projection operator once, what you get is this vector, which is in the 0 direction, right? A times 0. But now if you want to check the component of this vector in this 1 direction, what will you get? You'll get a 0, right? Because this vector is completely in 1 direction, in this 0 direction. Then in 1 direction it will have no component, right? So if you act on this psi with projection operators consecutively which are orthogonal to each other, then what you expect is that you'll get a 0. So let's prove that. So if you the projection operator pi 1 and pi 0, let's see what it is. So by definition this is 1, 1, and by definition this is 0 and this is 0. But we know that the inner product between 0 and 1 is equal to 0, then this is 0. Proved. All right, so what is the most general thing? If v and w are orthogonal to each other, then pi on w and then pi v, or vice versa, pi v pi w should give you 0. All right, so these are the two properties that we have to keep in mind, this one and this one, and we will use it in many applications of quantum computing. All right, so thank you so much.